Hello, everyone. Welcome you back to study MA4822, which is a course about the measurement and the sensing system. Today, we move on to study the lecture on measurement of a free flow rate. As usual, before we enter the study of today's lecture, let me give you a quick overview or review about the answer to these four common questions that you may have in mind. Question number one, why to study this course? Question number two, how to study this course? Question number three, what are you going to learn from this course? And the question number four, how to learn the knowledge from this course, right? So let me begin with the answer to this first common question that you may have in mind, which is about why to study this course. By now, you should know that our mission on Earth include, number one, to understand the world. Number two, to improve or to change the world. Then how to understand the world? The answer is to discover knowledge about the physical world on Earth or in the universe, right? And then how to discover knowledge? The answer is to obtain sensory data and the input, okay, to the process of knowledge discovery, right? Then how to obtain sensory data? Answer is to make use of measurement and the sensing system, right? Then how to improve the world or how to change the world? The answer is to invent smart products, smart machine, and the smart system. Then how to invent smart products, smart machine, and the smart system? The answer is to incorporate closed-loop feedback control system into the design of this system, this product, and this machine, all right? Then what is a closed-loop feedback control system? The answer is it is a system with three basic building module or three basic building block. And one of them is a sensor, all right? For example, in future city, we may want to deploy smart parking system, smart street lighting system, smart building system, smart home system, smart environmental system, smart healthcare system, and also to deploy Internet of Things. Then inside the Internet of Things, there are two major devices. One of them is a sensor, all right? So therefore, you see that this course is extremely important, all right? The second common question that you have in mind is about how to study this course. My recommendation to you is to put yourself into the mindset of a designer. Then in this way, you will be able to automatically raise this question. For example, who are the user? What are the needs from this user? What are the functionality of your product or your system that you are going to develop in order to meet the need of this user? What should be the solution behind the design of your future product or future systems, such as a sensor or measurement and the sensing system, right? So answer to question number one should be straightforward, okay? The user include human being because we want to understand the world. The user also includes smart products, smart machine, and the smart system, all right? Then what are the needs from this user? Their needs are the same, which is to have sensory data, right? Then what should be the functionality from your sensor or from your measurement and the sensing system? The answer depends on the specific nature of the user. For example, smart vehicle may need a certain type of sensor. Smart robot may need another set of sensor, right? So answer to question number three depends on the specific nature of the user, all right? Then what should be the solution behind the design of your product or your system? The answer is to study well this course. At the end of the study of this course, you will know the principle behind the design of your future sensor or future measurement and the sensing system, right? The common question number 3 that you may have in mind is about what are you going to learn from this course. Basically, this course covers the study of physical principle behind the design of a popular sensor in electric domain, in mechanic domain, in environmental system, and in intelligent system. In addition, this course covers the basic detail about the physical world, the basic detail about the conceptual world. This course also covers the basic knowledge for you to cope with the randomness in the physical world and for you to understand fuzziness in the conceptual world. All right. Then the 4th common question that you may have in mind is about how to learn the knowledge from this course. This slide basically shows you the general guideline for you to follow in order to learn the knowledge from this course, right? And you will see that the design of a sensor or measurement and the sensor system involve 2 basic steps. Step number 1 is to transform the value of a physical quantity under measurement into readable value. Step number 2 is to calibrate your sensor or measurement and the sensing system. In this way, the output from your sensor or measurement system is exactly equal to the value of a physical quantity on the measurement at the input. In addition, the unit of a measurement assigned to the output is the same as the unit of a measurement of the physical quantity on the measurement at the input. For step number 1, you may face 2 situations. The first one corresponds to the case in which it is good enough for you to make use of a front-end sensing element to transform the value of a physical quantity on the measurement into readable value. However, in most cases, you may face the second situation in which you have to make use of both the front-end sensor element and the back-end sensor element in order to transform the value of the physical quantity on the measurement into readable value. All right. So now we are ready to continue our study with this lecture on measurement of fluid flow rate, right? And in the previous lecture, we have studied the measurement of the physical quantity, which is related to the storage of the fluid, right? After the storage of the fluid, we need to distribute the fluid to location of consumption or consumer, because we need to have a fluid supply system, right? And the fluid supply system consists of storage of the fluid and the distribution of the fluid. Then for the distribution of the fluid, the important parameter is flow rate, because we want to charge the usage of the fluid or consumption of the fluid. Then how to charge, okay, your user for the usage of the fluid? The only way is to charge the consumer based on the consumed volume or consumed mass or weight, right? So therefore, you need to have an automatic sensor to measure the amount of consumption made by your customer, all right? So the measurement of fluid flow rate is extremely important inside the fluid supply system, right? And here you may ask this question, okay? How come there's another physical quantity called as a fluid velocity, all right? Actually, there's overlapping, because inside the fluid supply system, if you know the fluid velocity, if you know the density, then, and if you know the geometry of the pipe, okay, or tube, all right? So you should be able to calculate flow rate from the knowledge about the fluid velocity. However, there are situations in which we only want to know fluid velocity, all right? And even based on the knowledge of fluid velocity, we will not be able to determine the flow rate. And in that situation, anyway, we have no interest in knowing the flow rate. For example, we can use a fluid system to serve as a transportation system. For example, the ship, the boat, okay, can travel, move on the water surface, right? Then in that situation, we may want to know what will be the water's velocity, because the ship's velocity with respect to the water's velocity, with these two knowledge, then we should be able to know what will be the velocity of the ship with respect to the earth, okay, or to the ground, okay? So that is a typical scenario in which we only know, okay, the fluid velocity, okay? Then for this scenario, it's different because we want to charge the consumer about the usage of the fluid. Therefore, we need to know flow rate, John. Without the knowing flow rate, how could you charge, okay, consumer, okay, for the usage of fluid such as water, or gas, or fuel, etc. Right? So there's a slight difference. This is why we separate the lecture on the measurement of flow rate from the lecture on the measurement about the fluid velocity, okay? Because they are not exactly the same, and their application context may be slightly different. Also, they are a little bit overlapping, all right? Okay, but they are different there, right? Okay, so for this lecture, we focus on the measurement of a flow rate with the focus on the monitoring the usage of fluid, or to charge the consumption of fluid. All right. So here we are not focused on the use of a fluid system to support transportation. All right. For that application, we will discuss it in the next lecture. All right. In a separated lecture. All right. Okay. So let's start with the basic detail or the physics behind fluid flow rate, right? Then basically we need to know, okay, what is the definition of the flow rate? Okay, how many types of flow rate, okay, are there for us to pay attention, right? So you may have this question in mind: is the fluid flow important? The answer is yes, because the fluid supply system include two components. One is the storage. Okay, for fluid storage, important parameter is the level. We want to know the percentage of the fluid inside the tank, or inside a container, etc. Right? When you store the fluid, basically we want to distribute it to the user, or to the consumer. All right. Then the second component of the fluid supply system should be the distribution system. Then how are we going to distribute the fluid in the space so that the fluid could be reached the location of a user or location of a usage, right? The answer is to use a piping system or distribution system. And inside the distribution system, then automatically you will see the flow of fluid, right? So in this picture, then you see, okay, we have a storage tank, and we also have a very, very complicated piping system. And then you see, you may ask yourself, how come there's so many pipes there? Answer is what? To distribute, okay, the fluid from the tank to the location of consumption or usage, right? So that's it. So without the flow, there will be no supply of a fluid system. Clear, all right? And in the society, in industrial, there are many applications with the use of free supply system. Okay, for example, in chemical plant, so this is a typical example. All right, so chemical plant basically is to transform material in liquid state. Okay, into the material in liquid state at the final stage. So you have material in liquid state at the input state. Then after all the transformation through the chemical reaction, whatever, then the material will become liquid state or eventually become material in solid state, okay, at the output. So that is kind of a chemical manufacturing. So you have an input material at a certain state, output material at another state, okay? So in the case of a chemical plant, at least input should be material in liquid state, output could be material in solid state, liquid state, or gas state eventually. All right. So then we need to have a storage for liquid and the distribution for liquid, right? Then for hydropower station, it's the same. We can make use of water flow, okay? Storage of the water at a certain altitude, then the water contain potential energy, then transform the potential energy into kinetic energy, then kinetic energy into electric energy. So this is a basic transfer of energy from potential energy to kinetic energy to electric energy, right? So this is typical application with free supply system, right? Then in our home environment, okay, except in the village, all right, in the remote area, but in city, okay, all the apartment, all the houses has a water supply system, right? And especially the supplier of water, okay, must charge the usage of water by the resident. So the water usage is not free in today's situation, maybe free in future, okay, but now it's not free, okay? So you must pay for the usage of water in your home or your apartment, etc. All right, so this is a typical application, right? So then this video may reinforce your idea about the
improving access to resources while preserving and replenishing those resources is what we do at Veolia. Each day, our distribution systems deliver drinking water from treatment plants to our customers' taps. These systems are designed to provide an uninterrupted supply of drinking water on demand, compliant with regulations, in line with customer expectations, and with minimal environmental impact. Here's how and why at a glance. Drinking water travels directly from treatment plants to households via pressurized mains. Depending on the topology, we can also pump water into high storage tanks so that the water flows through the system via gravity. The distribution network branches out towards each user's connection point. Special devices and equipment help to regulate water pressure according to fluctuating levels of consumption. Pipe diameter and material is adapted according to the local constraints and the characteristics of the water. The system is managed in small zones, which makes it easier to diagnose problems, do maintenance work, and accurately measure water distribution and consumption volumes. This is how we identify water losses. Leaks are found thanks to acoustic detection techniques or utilization of a tracer gas. At the base of buildings, pumping stations boost the water pressure so that it reaches every floor. We sample and analyze water throughout the network on a daily basis, making water one of the most closely monitored products made for human consumption. Measuring instruments, sensors, and probes are installed at key locations throughout the system. Meters measure water consumption at each household. In the network, other meters and instruments provide real-time readings on the flow rate, pressure, vibration levels, and water quality, and detect any leaks or changes in quality as soon as they occur. These instruments transmit data via communication systems. This is what makes drinking water systems smart. All the data converges at a centralized control center. These control centers combine and analyze the data to provide insight about operations or events. This way, analysts have a global view of the network in real time. This is how they can monitor water quality, improve the operation and maintenance of the system, and respond rapidly and transparently, keeping authorities and consumers in the loop. By ensuring a continuous supply of water, while constantly optimizing our network's performance, our solutions are a long-term guarantee of operational efficiency for cities and for customers, the assurance of high-quality yet affordable water.
All right, so you understand the water supply system in modern city is a very important infrastructure, all right? And surprisingly, if you look at yourself inside your body, automatically you will agree that the inside our body, blood supply system is extremely important, all right? So without the blood supply system, we cannot survive. Then you can start to think about the blood storage organ and the blood distribution channel, all right, or piping system. So you will see, basically we have two inside our body, two system. One is to pump out, okay, the supply. One is to recycle, okay, the use the blood, okay. So the supply blood is called oxygen-rich blood, okay. So our lung in the oxygen, okay, inside the blood, okay. Then the recycled blood is deoxygen-rich blood, okay. So then we must recycle the blood, okay. So in or oxygen, right? So these are the major function of blood supply system inside our body. And then you can see the network is very complicated, all right? Because the blood could be supplied to every part inside our body. So this is extremely complex fluid supply system. And in this case, the fluid refer to blood inside our body, all right? Okay, so it is very important for us to know, okay, the fluid distribution system, all right? So therefore, we need to know a little bit, okay, the property and the nature of a flow of a fluid inside the pipe, right? So basically, we have two types of flow. One is called laminar flow, another is turbulent flow, right? And on the normal situation, in the steady state response, the flow should be laminar flow, okay? So assume there's no more turbulence when the transient response die off, okay? So everything becomes steady state. And another thing for you to know is about the velocity distribution at the same section, closed section inside the pipe. Normally, the velocity is not uniform, okay? And at the location which is close to the inner surface of the pipe, velocity will reduce. This is due to viscous friction, okay? So it's also for you to know, okay? So you cannot assume the uniform distribution everywhere, okay, inside the section area, right? So when you do the measurement, it's good for you to pick up, okay, the value at the meter of the pipe, right? And when there's a flow, and if you place an object inside the flow, then this object will pick up a drag force. So this is a very useful phenomenon for us to design the sensor, right? So we can put a sensing element here, then this sensing element may receive a drag force, right? Then this drag force could be converted into voltage or whatever, right? So this is one useful phenomenon for us to know, right? And I guess every one of you have experience about the drag force, okay? When you walk on the street, when there's a strong wind come in front of you, then you will see there's a pushing force, okay, in front of you. That is a drag force, okay? When you drive your car, it's the same, your vehicle will constantly receive a drag force from the air, right? On top of that, if let's say we place a sensing element with a hole, okay, And inside we may have gas, air, or liquid. Then the force applied on the unit area will become a pressure. Then the pressure will push, okay, the liquid inside the tube, okay, to move up or move down. It depends on the pressure difference at this point and at this point, right? So then you understand there's a drag pressure, okay? So drag pressure is a drag force per unit area. That's it, all right? So we can also make use this phenomenon to design sensor element, okay, to pick up a value which is proportional to velocity, all right? So this is a physical phenomenon, okay, for us to apply in order to guide the design of flow rate sensor or velocity sensor, whatever, right? And when the fluid supply system reach the steady state means no more turbulence, everything is very smooth there. Then we have this continuity phenomenon. Okay, basically it also means a Bernoulli equation, right? So it means the sum of these three terms is equal to constant, all right, at any point inside the fluid system. For example, at this point, the pressure at this point plus density times the height of this point and the gravitational acceleration plus 1/2 density velocity square. So the sum of these three terms is equal to constant. Constant means you maintain continuity everywhere is the same, right? So this is also very important. Okay, so we may apply this knowledge to guide the design of a sensor or to undertake computation in order to derive the flow rate or velocity of the fluid, right? And when there's a supply of the fluid, then we need to monitor, okay, or charge the consumption. So at the beginning, I already mentioned. So this is the context of application for us to design measurement and the sensing system for fluid flow rate. Okay, so this is the major focus or application context. Okay, so we need to monitor the consumption. We need to charge the consumption. All right. Then in practice, now you understand, we could charge the consumption by volume. So usually you top up the fuel, okay, in the petrol station, and you pay the price in terms of dollar per liter. The liter is a volume, right? And for some scenario, we may charge the consumption based on the amount of masses, all right? But in most cases, we will charge the consumption in terms of amount of volume, all right? Because this is a common practice, all right? Okay, then this video basically, okay, help you to understand, okay, this application context. So this is a very big market in the world. With the use of flow rate meter, then eventually we can develop a smart city management system, right? So this is a typical example of linking sensory data to intelligent decision making. right, so you understand, okay? So we need to monitor and charge the consumption of fluids such as water, gas, and eventually the petrol, okay? Depends whether it's in the factory or in the home environment, etc. Right? Then this example basically showing you the familiar, okay, situation to every one of us, like as long as you have a vehicle or car at home. So regularly you must top up, okay, the fuel tank, all right? Then you understand you must, every time when you pump, okay, the fuel tank inside your vehicle, and you must pay a price to the petrol station, all right? And this is a typical scenario of charging the consumption of fuel in terms of amount of volume, right? And inside the petrol station, then you will see on the ground there is a huge storage tank, right? And this storage tank also need to be top up, right? When the fuel inside the tank go to a very low level, then the supplier will come and to top up this tank. And here we also need to monitor the amount of fuel has been pumped into the underground tank, because the supplier of the fuel here will charge, okay, the petrol station channel, because it's not free, all right? Then for individual passenger vehicle, once you drive in, so you will take fuel from the underground storage tank and then pump the fuel into the tank inside your car. Because inside your car, you see, you also have a storage tank there. And we also, inside your vehicle, there's a meter to monitor the level of fuel inside the tank. And in the dashboard of your vehicle, you should be able to see, okay, how many percentage of the fuel left, etc. Okay, so then based on the reading of the level of the fuel inside the vehicle's fuel tank, then you can make a decision on whether you want to drive into the petrol station to top up the fuel or not, right? Okay, so then you will see normally petrol station may have many dispense machine dispense the fuel, all right? So these are quite complicated instrument, but in particular, there must be a flow meter there, flow rate meter, because otherwise the petrol station do not know how much fuel has been pumped into the storage tank inside your vehicle, all right? So then you understand, okay? So every dispense unit must have a flow rate meter, okay, to calculate the amount of fuel, okay, consumed or taken by you, okay. So based on that amount of fuel, okay, so you must pay a price calculated based on that number, all right. So this is a typical scenario for you to know. We need to measure flow rate, all right. And of course, in every home, every flat, every house, like in a modern city, every household must pay the price of water consumption on monthly basis or quarterly basis, etc. Okay, so this is a typical example. And in the environment, okay, we may also want to monitor the flow rate. Okay, and in order to prevent the flood, okay, if let's say during the rainy season, there are so many water flow everywhere, okay, then we must pay attention, okay, make sure the flow rate will not exceed the storage capability within the city, within the province, etc. Otherwise, the flood will come out, all right? Then it will cause damage to the resident or to the farm, etc. Right? So then this video show you, okay, the manual way for you to roughly estimate the flow rate in the river. However, then you understand that we can actually implement the automatic measurement system for flow rate in river, right?
Measuring the flow of a stream is important to understanding how much water is at a certain point at a certain time. Flow can be calculated using the float method with a measuring tape, small plastic bottle, and a timer. Flow is best measured in a run where water is flowing and when there are two observers. First, determine the float distance by measuring and marking 2 points along the length of the channel. Try and get at least 10 feet. This length will be your distance. Next, measure 3 depths across at the channel cross section. Average those 3 depths, and this is your depth. Next, measure a representative width of the stream, and that will be your width. Now let's float the bottle. Partially fill the float bottle with water. One observer stands at the top of the reach, and the second observer stands at the bottom. The observer at the top tosses the float bottle into the channel and calls out "start" when it crosses the upstream point. The other observer will start the timer. And as soon as it crosses the second point, they'll stop the timer. Repeat this toss process 3 times and average the 3 times together. Use this average as your time entry. Now you can determine the flow in cubic feet per second by multiplying the width and average depth by the product of the distance and the time. A correction factor is commonly used because surface flow is faster than flow in the water column.
All right, so that gives you an idea about how to do the measurement manually, and immediately you can think about the way to improve this manual measurement with automatic flow rate sensor, right? Now, also you may want to know what is the definition of flow rate. Since we have a flow rate in terms of amount of volume, we may also have a flow rate in terms of amount of masses. Therefore, what should be the exact definition of flow rate? So actually, we have 2 types of flow rate. One is called volumetric flow rate, another is called mass flow rate, right? So volumetric flow rate basically means the amount of volume passed through a point per unit time, all right? For example, at the T1, let's say we use location A2 as a reference point, all right? So T1, then at the T2, so we have this amount of volume pass through A2, right? So then this volume divided by the time, T2 minus T1 will give us the average flow rate or average volumetric flow rate, right? Then what should be the volume here? The volume should be equal to the sectional area, A times the distance traveled by the flow, right? So that gives us the volume. Then for this amount of volume, the traveling time is from T1 to T2. So therefore, T is equal to T2 minus T1, all right? Then from here, you will see this is the travel distance from T1 to T2. This distance divided by T is what? Is the flow velocity, all right? Then flow velocity times area give us the volumetric flow rate. So this is a definition of volumetric flow rate. Then what is a mass flow rate? Because for some application, we may charge the consumption based on the amount of masses of the fluid, right? Then in this case, we want to know, okay, within this amount of time from T1 to T2, what should be the weight of this volume, right? Now we understand the weight of the fluid, okay, is equal to the volume times density. This could be the density of the water, density of the gas, density of fuel, okay? So that means the volume times density correspond to the mass of this volume. Then traveling time is what? From T1 to T2, then divide by T. T is equal to T2 minus T1, right? Then this is consumed mass per unit time, right? So this is a consumed mass per unit time, right? Now here you see D divided by T again is flow velocity. Then we have density times area times V. So we use this notation. This is the first order derivatives of the mass or variation of the mass, right? So we use this one to represent the mass flow rate, right? So now you know the equation, okay? So it means inside the fluid distribution system, the important parameter will be volumetric flow rate or mass flow rate, right? And this is just a small exercise for you to know, all right? So for the fluid supply system, okay? So we have a two component. One is a tank for storage, another is a pipe for distribution. Then here you see we have a 4 tank, and we also have a pipe for distribution. Here you have a pipe, here you have a pipe, here you have a pipe. Then we have a source to supply the fluid. Then, okay, this is just a small exercise for you to practice with your brain, okay? Then this is also exercise for you to think, okay? And help you to understand the fluid supply system, and therefore you may enjoy your work, all right? So for this case, which tank will fill up first? In this case, which tank will fill up first, okay? Try to discuss among yourself, all right? Okay, then challenge you, all right? Okay, so that's the physics behind fluid flow rate, or the basic equation for us to use in order, okay, to calculate, okay, the flow rate. Now come to the major part of this lecture, okay? Now we want to know how to indirectly measure fluid flow rate and how to directly measure fluid flow rate, all right? So first scenario corresponds to the case in which if we know the related parameter, all right, then we can calculate fluid flow rate. However, the second case should be our major focus, because this course is for you to learn the physical principle behind the design of a measurement and the sensing system. So therefore, we want to know how to directly measure fluid flow rate, all right? So let's start with indirect measurement first. So here, indirect measurement means computation, right? So this is the first example, right? So let's say we have a water supply, okay, outside, okay, and assume this is a water tank in your home, all right? So then we need to calculate, okay, the water consumption, okay, how the amount of water you have a top up into your house water storage tank, all right? So the tank section area is given to you 50 meters square. The water level increase at this rate 10 centimeter per minute. Then what is the volumetric flow rate of an inlet pipe, right? Because the supplier may charge you, okay, based on the volumetric flow rate, right? Something like that. So then by definition, volumetric flow rate is equal to the ratio between variation in volume divided by the duration in which this variation occurs, right? So variation in volume is equal to the sectional area times the height, because here we just calculate variation of a volume inside the tank, because this variation comes from the pipe. So this is another way to calculate, okay? So we just look at the variation inside the tank, all right? And this variation comes from the pipe, right? So because the question only tell you the increase of water level, okay? Then we should be able to calculate variation of volume, okay? So variation of volume should be equal to the sectional area of the tank plus the increase, the level rate increase per unit of time, because the question tell you per minute increase by 10 centimeter. 10 centimeter equal 0.1, 1 minute equal to 60 seconds. So you see, pay attention to the unit conversion, right? Sectional area is this one, all right? So then you just calculate. So this is volumetric flow rate already 0.025 meter cube per second, right? So if let's say you pump in, okay, or top up this tank for 1 minute, then times 60, then you know the volume taken by you by your house, right? Then you must pay the price accordingly, right? So here is a second example, all right? So now is this corresponds to the situation that we consume the fluid from a storage tank, right? And the question tells you the density inside the tank, there is water density is 1,000 kilometer per meter cube. So then the level inside the tank decrease at least level change rate. This you consider this is a level change rate inside the tank. Okay, 5 millimeter per second. Section area of the tank is given to you. Then what is the mass flow rate at the exit of the outlet pipe, right? So mass flow rate is equal to the ratio between variation of the mass of the water divided by the duration in which this variation occurs, all right? So variation of the mass equal to volume times density, okay? So this is the density. Volume is equal to area, section area times the level change rate, okay? So level change rate is this one, and the question tells you level change rate is 5 millimeter. So you must do the conversion. 5 millimeter per second is equal to 0.005 meter per second. All right, section area 25 meter square, and the density of the water 1,000 kilogram per meter cube. So you put in the value, then you will see, okay, the consumption of the water is 75 kg per second, right? And this is a example, right? So in this case, we let you know that the pressure at the point 1, so you see we have a point 1, point 2. So we assume we know the pressure at the point 1, pressure at the point 2, and the section area at the point 1, point 2 are also given to you. There's a A1, A2. Now we want to know in this generic setup, what should be the formula for us to calculate volumetric flow rate inside the pipe, okay? So this example basically is for us to prove a formula, because that formula is useful to us, all right? So basically it's for you to prove this formula, right? So then here we apply the continuity equation, basically is a Bernoulli equation, okay? So then, okay, in this case, it's not Bernoulli equation, continuity, but here is a continuity in terms of volume, because there's no leakage of fluid. So therefore, that means the amount of fluid pass through point A, point 1 should be equal to the amount of fluid passing through point 2. So that means the volume pass through point 1 is equal to section area at the 1 and the flow velocity at the point 1. Then this should be equal to constant. So volumetric flow rate equal to constant. Okay. So continuity here means this one. Okay. So Bernoulli equation is another equation of continuity. Okay. So this one is more or less like a conservation of fluid inside the pipe, as long as there's no leakage, as long as there's no additional top up. All right. Okay. So then there's a continuity of or conservation of flow volume inside the pipe. All right. So then from here, then we both sides divide by A2, then swap the equality, then V2, then equal to A1 divided by A2, V1. Then we apply another continuity equation. So that is a Bernoulli equation. So it means at this point, the sum of the 3 terms must equal. Since point 1, point 2 are the same height, so there's one common term, okay, which is related to H, will cancel out because they are at the same level, all right? So then we only have 2 different terms. Pressure at the point 1 plus, it's more or less like the kinetic energy. The point 1 is equal to the sum of the pressure at the point 2 plus, this is, looks like a kinetic energy at the 0.2. Okay, now we substitute. Okay, from this equality, so we shift this one to the right-hand side, this one to the left-hand side, then we swap the equality. Then we have a V2 square minus V1 square equal to P1 minus P2 divided by rho density times 2. Because, okay, because these are the coefficients in front of V2 square minus V1 square. Okay, and then both sides divide by this. Then we swap the equality. Then we have this equality. Now we replace, substitute V2 with this result. All right. Then here you see V2 is a function of a V1. Then here we have a V1 square, take it out. Okay. Then both sides divide by the coefficient in front of a V1 square. Then we compute square root. Then we have equality or formula for us to calculate V1. So you see square root inside here is the pressure difference between 0.1, 0.2, and this is the area ratio between 0.1, 0.2. This is the density. From here, you will see actually these are the constant because once the pipe has been designed, we will never change it. It's a constant. Once install the pipe on site, all these are constant. All right. If let's say this is a water flow inside, we never change the type of fluid. Okay, density is a constant. So actually you see this one is only proportional to pressure difference, okay, between these two locations. Then what will be the volumetric flow rate? Volumetric flow rate is equal to the section area times flow velocity. Okay, so you remember this equation? This equation, okay? So basically apply this formula, all right? So then the volumetric flow rate is equal to area times V. Then substitute this one with this result. Then you have A1, A2 times square root. Okay. So this is measurable, P1 minus P2, because the rest are constant already. All right. So then we have this formula done already. Then this example is showing you how to apply this result to do calculation. Let's say for whatever reason, now we know the difference between P1 and the P2, okay? And then what should be the volumetric flow rate, okay? So in this example, we have a vegetable oil flow inside the pipe. Density of vegetable oil is this one. Section area is 25 centimeter square, okay? At the point A, and the section area at the point A1, this is A1, this is A, is 9 centimeter square. If the pressure difference is 0.1 atmospheric pressure, then what is the volumetric flow rate inside the pipe? So from this equation, then you see A1, A2 are given to you, P1 minus P1 is given to you, all right? Density is given to you, okay? Straightforward, just put in the value, then you calculate, you get this answer, all right? But here you must pay attention. We use a basic unit of a measurement for pressure. Atmospheric pressure is not the basic unit of measurement, is Pascal, right? So you must convert this one into Pascal. So it's this one. So it's 0.1 times 103,325. All right. So then you should be able to get this answer. All right. So you should not put the 0.1 here. Ignore this conversion. Then you'll get wrong answer. All right, so this is just for you to know. Okay, that is the basic way for us to do indirect measurement of a fluid flow rate. Then our major focus is on the study of the physical principle, which will guide us to design direct measurement and the sensing system for fluid flow rate, right? So what should be the principle for us to follow? So actually there are many principles. Okay, here we are going to study these 3 popular ones. Okay, these are not the only one. Okay, there are many others. All right, so these 3 are popular one. Okay, so we just study these 3. It should be good enough for us to follow in order to guide the design of your future measurement and the sensing system for fluid flow rate, right? The first one is to consider fluid is electrically conductive. So it is true because water is electrically conductive. Therefore, for any mixture, okay, mixture of a fluid inside, there is a presence of a water, then such a fluid is conductive, all right? For conductive, then we can imagine water is a conductor in liquid state because we have a conductor in solid state. And when this conductor plays inside magnetic field, when there's a movement, so it is equivalent that the electron inside the atom of substance, okay, which consists of the conductor, will undergo movement. So that means you have a lot of a flow of electron. Then this flow of electron will receive induced force by the presence of a magnetic field. So idea is to apply magnetic field. Okay, then let the electrically conductive fluid to pass through. Then magnetic force will be induced, will act on the electron. Then electron will start to move in the perpendicular direction. Then you will see, okay, the charges will build up at the least electron and the least electron. Then there's a voltage. So this is a typical scenario of converting flow rate into voltage. Then we can measure voltage, then get the computer readable value. Then after calibration, we can relay the output value to the value of flow rate. All right, so this is the first principle for us to follow. Second principle is for us to apply this equation. Okay, follow this one. So you see the flow rate is related to the pressure difference. So that means if we are able to measure this value, that means what we should be able to get the value which are related to flow rate. Then by calibration, then we can make the output to be exactly equal to the input. So that is the second principle, all right? Just now we have already played with the equation. The third principle is quite interesting, all right? So we just inject thermal energy into the fluid. When there's no flow rate, okay, then distribution of the temperature should be symmetric. All right, then the reading from these two temperature sensor, one is at the upstream, one is a downstream, then should be equal because even distribution. When there's a flow rate, then the distribution will not be the same. Okay, then the difference between these two temperature give us an indication about the amount of flow rate. Okay, so it is quite straightforward for you to understand. All right, so then, okay, we are going to look into the detail, okay, of implementation. For example, now we want to apply principle one, then how to design the sensor. So again, you see now we leverage on this supply of a microcontroller, right? Because all microcontroller are programmable sensor of a digital voltage or digital sensor of a voltage. So we leverage on the supply of a microcontroller in the market. Then our focus is just to convert flow rate into voltage. Okay, then the voltage could be the input to the microcontroller, right? Then the focus is how to convert flow rate into the voltage, right? So then this solution is to, at the measurement section, apply the electromagnetic field. Then if the fluid is electrically conductive, then the voltage will build up in the perpendicular direction, okay? Then we have a reading of the voltage, then the reading of voltage will be the input to the microcontroller, okay? So this is a quite straightforward design solution for us to follow, all right? And here you will see the voltage actually build up at the two electrons is proportional to the density of magnetic field, proportional to the flow velocity, and also proportional to the distance, okay, between these two electrons, okay? Then here you may ask this question, okay, how do we know the density? So actually calibration will take care of that, okay? Because density is just a scaling factor. Let you see density could be captured by K. K is a coefficient, okay? You can capture okay, absorb any constant parameter, right? Then by calibration, we can, okay, find out the one-to-one relationship between input and the output, all right? Get the calibration equation. Calibration equation will take care of the value of density, all right? And then this video show you implementation, all right?
The most diverse substances are transported and distributed in piping systems every single day. They may include drinking water, fruit juices, chemicals, or even slurries containing stones. The fluids flowing through pipes often have completely different properties. Consequently, there are different principles for their measurement. One method is flow measurement based on the electromagnetic principle. The basic physics of this principle can be traced back to the English physicist Michael Faraday, who in 1831 discovered that electrical current can be generated with a magnetic field. Roughly 100 years later, the Swiss inventor and priest Father Bonaventura Tirlemann applied this knowledge to electrically conductive liquids flowing in pipes and built the world's first electromagnetic flow meter. Let's take a closer look at how this measurement method works. Two field coils are located inside each electromagnetic flow meter. With the help of what are termed pole shoes, these coils generate a constant magnetic field over the entire cross-section of the measuring tube. Two electrodes which can pick up electrical voltages are installed at a right angle in the wall of the tube. The lining fitted on the inside wall prevents electrical short circuits between the conductive liquid and the metallic tube. If there is no liquid flow, no induced electrical voltage is measured at first between the two electrodes. The electrically charged particles of the conductive liquid are evenly distributed, shown here in water with red and blue particles. However, as soon as the liquid starts to flow in the measuring tube, the magnetic field applies a force to the charged particles. As a result, the positively and negatively charged particles in the liquid are separated and collect on the opposite sides of the tube wall. Now an electrical voltage forms, which is detected and measured by the two electrodes. This voltage is directly proportional to the flow velocity in the pipeline. Together with the known tube cross-section, the flow volume can then be calculated. The greater the flow velocity, and thus the separation of the charged particles, the greater the electrical voltage between the electrodes. The electrodes also detect what is called interference voltage, which has to be separated from the actual measuring signal. One method that has been successfully used for this purpose is to create the magnetic field with a pulsed direct current. To do so, the polarity of the magnetic field is alternately reversed, illustrated here in slow motion. The voltage picked up on the measuring electrodes now constantly changes in polarity. As a result, all constant interference voltages can be eliminated. For example, electrochemical effects in the liquid, or external electromagnetic fields. Thus, the size of such interference voltages has no impact whatsoever on the actual measuring signal. The advantages of this are a stable measurement and a stable system zero point. With an installed base of over 1 million electromagnetic flow meters.
So this should be good enough, right? So you see the example of implementing principle 1, right? Then principle 2 is to make use of the pressure difference, okay? Because the pressure difference is related to the flow rate, all right? Then how to create the pressure difference? The idea is to change the diameter, because when we change the diameter inside the tube, then flow velocity will be different. So higher the flow velocity, lower the pressure, lower the flow velocity, higher the pressure, then we create a pressure difference. Okay, so when everything reaches the steady state, then we should be able to get the reading, then get the value, then that value is related to the flow rate. Then after calibration, then we can make sure that the output value is exactly equal to the input value. From here, you see calibration is very important. Even in the previous video, all right, the intermediate value, the output from the sensing element may relate it to flow velocity, something like that. But after calibration, we can take into account the density and the sectional area, whatever, all right? Then make sure that the output value is exactly equal to the input value, right? So that is the magic of doing calibration. Then for this one, it's the same, okay? So we create the pressure difference, then we pick up that value, okay? We just need to know a value which is proportional, either linearly proportional or non-linearly proportional to the value of a physical quantity on the measurement. Good enough. Then by calibration, then we can rectify all the internal relationship and make sure that the output equal to exactly the input, right? So then in this case, first we need to convert the flow rate into the pressure, then pressure into the voltage, right? And in one of the previous lecture, we have already studied measurement of pressure. So therefore, the focus here is how to convert flow rate into pressure difference, right? So then in this way, then we should be able to get the voltage, then supply voltage into the microcontroller, because here microcontroller is programmable digital sensor of voltage, right? So this is a guideline for us to apply principle 2. Then you may want to know, okay, how to convert flow rate into differential pressure. So the popular solution is to use this Venturi pipe, all right? So you see the Venturi pipe will gradually change the diameter. Then in this way to prevent the formation of turbulence, right? So to make the fluid system to remain at the steady state, right? Then at the 2 locations, so you will see the flow rate here will be slow, velocity will be slower than the velocity at this point. Then the pressure at this point will be lower than the pressure at this point. So here you have a high pressure, here you have a low pressure, right? So then in this case, you can use a sensing element to pick up the pressure difference. Then this pressure difference could be converted into voltage, right? So the mathematics, okay, is this equation. So you see the pressure difference is directly related to the flow rate. If we are able to convert pressure difference into the voltage down already, okay, then we get the value which is related to the value of a physical quantity on the measurement. Then by calibration, then we can rectify, okay, the non-linearity between these 2 values. Then finally, we have one-to-one or have a straight line which pass through the origin and have an angle which is 45 degrees above the horizontal line. So then in this case, it means the output is exactly equal to the input. All right, so this is a solution. And then this video show you the implementation with principle 2, right?
Substances are transported and distributed in piping systems every single day. They can include solvents and chemicals, oil and gas, or steam for energy transmission. The fluids flowing through pipes often have completely different properties. Therefore, different principles for their measurement are required. One method is flow measurement, based on the differential pressure principle. Some 300 years ago, Swiss mathematician and physicist Daniel Bernoulli discovered the direct relationship between the pressure and speed of a fluid flowing in a pipe. Italian physicist Giovanni Battista Venturi also performed experiments on flow, and in 1797 he built the first flow meter for closed pipes, known as the Venturi tube. Here is how this measurement method works. Differential pressure flow meters have an artificial restriction integrated into the measuring tube, illustrated here by the example of an orifice plate. Two holes are located in the pipe wall, one before and one after the orifice plate. Two separate tubes connect these holes to a differential pressure sensor with its two pressure chambers separated by a diaphragm. The tiniest pressure differences in the flowing fluid can be precisely measured. If the fluid is not flowing, the pressure before and after the orifice plate is essentially identical. As soon as the fluid starts to flow, its velocity around the orifice plate increases significantly because of the restriction in the cross-section. At the same time, due to the laws of fluid mechanics, the static pressure at this point decreases. Consequently, different values are detected in the pressure chambers of the sensor, a higher pressure before and a lower pressure after the orifice plate. This pressure difference is a direct measure for the flow velocity and thus the mass and volume flow in the pipe. The higher the flow velocity and the resulting drop in pressure around the orifice plate, the greater the differential pressure measured. In numerous industrial applications, the orifice plate covers many needs of flow measurement technology. However, other designs are available for certain measuring tasks to minimize undesired effects, such as excessive pressure loss or abrasion of components due to solids carried in the fluid. This demonstration shows that an abrupt restriction generates severe turbulence in a fluid. Nozzles with a rounded, funnel-like inlet clearly reduce turbulence and thus create less pressure loss. Nozzles are particularly suitable to higher flow velocities or to fluids with abrasive solid particles. Turbulence reduction is even greater with Venturi nozzles. And finally, with Venturi tubes, where the restriction is created by longer conical constrictions in the pipe wall. All these designs can be supplied with different restriction diameter sizes, so that the pressure loss and the differential pressure generated can be optimized for the process conditions. Industrial flow measurement using differential.
So let's show you a typical example of implementing principle 2. And there are other solutions for you to tap, okay? The differential pressure, right? And in the video also it mentioned to you, okay, this scenario, right? And also you can apply, follow these two scenarios in order to get the pressure difference. As long as you get the pressure difference, which is a function of flow rate, should be good enough, okay? So then you get the intermediate value. After calibration, then you know exact relationship between output and the input. That's it, all right? So there are many design solutions, all right? Okay, then how to apply principle 3 in order to guide the design of a measurement and a sensor system for free flow rate, okay? Principle 3 is to convert, okay, flow rate into temperature distribution by measuring the temperature difference. Then we get the intermediate value. Then after calibration, then the output could be exactly equal to the input, right? So this is another very interesting, useful principle for us to follow, right? So flow rate convert into temperature distribution, because we know that we are able to convert temperature into resistance, and then resistance into voltage, all right? So in one of the previous lecture, we have already studied the measurement of temperature, right? So then we can leverage on that, okay, principle of measuring temperature to achieve this design of measuring flow rate, all right? Then you want to know, okay, how to convert flow rate into temperature. So actually, there are different solutions. One of them is to place a heater outside the tube. Then there's a transfer of the heat. And in the upstream, we have a temperature sensor. In the downstream, we have another temperature sensor. If there's no flow of a gas or liquid, then the temperature distribution should be symmetric, okay, centered about the heater, all right? And when there's a flow, let's say from upstream to downstream or downstream to upstream, then the distribution will not be symmetric, okay? Then the reading from the two temperature sensor will be different. So the difference basically give us a reading about the value of flow rate. That should be good enough. Then by doing calibration, then we should be able to find out the one-to-one relationship, all right? Or exact equality, okay, between output and the input, right? So this is a solution for us to convert flow rate into temperature profile, okay? Then in practice, we can place a heater outside the tube or place a heater inside the tube, all right? And we can also just have the heater plus single temperature sensor. And then you will see, okay, in the next slide, we are showing you a video which, okay, give you innovative implementation of principle 3, right? So, and in the video, basically, we only have one heating element and one temperature sensor. And the idea, I guess, is to maintain the temperature sensor to be at the constant value. Then, in order to do so, okay, if the flow rate is very, very high, then this one will lose temperature very, very fast. Then we need to top up the thermal energy, then increase the current. Okay, then in that way we know, okay, what should be the value, the wattage value or current value to A in order to maintain this temperature to be constant. Okay, so this is another way to get the value which is related to the flow rate. All right, so then this video will show you the detail about this innovative implementation, okay, which apply principle 3.
The most diverse gases are transported and distributed in piping systems every single day. They can include air in the water and wastewater industry, carbon dioxide in food and beverages, nitrogen and oxygen in pharmaceuticals, or natural gas for boilers and burners. The gases flowing through pipes often have different properties caused by changing process conditions. Therefore, different operating principles are required for their measurement. One principle is flow measurement based on the thermal principle. The basic physics of this principle can be traced back to the Canadian physicist Louis Vessel-King. In 1914, he mathematically described heat transport in flows. Here is how this measurement method works. Inside thermal flow meters are two temperature sensors protruding into the measuring tube. They're known as PT100 resistance thermometers. One of these temperature sensors measures the actual gas temperature as a reference, regardless of the flow velocity. The second temperature sensor is heated constantly via electrical energy, so that a predefined temperature difference is maintained between the two sensors. For example, 10 degrees. If there is no flow, the differential temperature between the two sensors does not change. As soon as the fluid begins to flow in the measuring tube, heat is drawn from the heated temperature sensor via the gas flowing past. The heat then is carried off by the flow. The corresponding cooling effect is measured and compensated immediately by adding more heating current. As a result, the target temperature difference is continuously maintained. The heating current required to maintain the temperature difference is proportional to the cooling effect. and therefore is a direct measure for the mass flow in the pipe. The greater the flow velocity, and therefore the additional cooling of the heater sensor, the greater the heating current required. An alternative adaptation of the principle keeps the heater current at a constant value, and then measures the change in temperature differential. But how is the heat actually transferred from the heated temperature sensor to the gas flowing past? This sequence shows that the heat is transferred by the gas molecules themselves. When the gas flows past, the molecules absorb tiny heat packets and carry them along with the flow. The faster the gas flows, the more often they absorb the heat. The heat transfer also depends on the density of the gas because at a higher pressure or lower temperature, there are more gas molecules in the pipeline. The greater number of molecules results in more contact with the heated sensor, meaning increased cooling and thus increased heating current flow. And finally, the heat transfer is also affected by the thermal properties of the gas. For example, at the same mass flow, the high thermal conductivity of hydrogen, shown here in green, causes cooling that is 100 times greater than with air. For a precise measurement, it's therefore important that the specific properties of the gas are known and are consistent. Flow measurement using the thermal principle is also possible in large pipes and ducts. There are meter types designed specially for this application. They can be inserted directly into the pipe via a standard process connection. It is important that the required insertion depth be respected so that the measurement is carried out at the correct point. For that reason, it's essential to program the actual internal pipe diameter for all insertion meters. Correct insertion also applies for rectangular and square ducting, often found in factory or building air circulation systems. With thermal mass flow meters from Endres and Hauser.
All right, so it should be good enough, right? Okay, this slide is just for you to think about how to measure flow rate inside our body. All right, so we also want to monitor, okay, the health condition, because the health condition could be reflected by the variation in the flow rate of our body's blood, right? And then you will see this interesting phenomenon because our heart is like a bomb. Okay, it suck in and push out the blood. Okay, then the vein will undergo periodic contraction, expansion, and this will produce these kinds of pulse. Right. So could we design a lighting system and then let our the blood to reflect the light, and therefore we put the light detector there, and in this way we convert the flow rate into digital pulse as output. All right, so come out the device like this. So this is a project for you to think about. All right, then if you are interested in, why not you treat this as a project assignment, come out the detailed solution, and then you virtually do a little bit of testing. All right, okay, so this is a project for you to know, okay, to consider. Okay, so after the design of a sensing element, the second step is to do calibration, because it's very important to calibrate the sensor so that the output value is exactly equal to the input value. In addition, the unit of a measurement assigned to the output is the same as the unit of a measurement of the physical quantity on the measurement. All right. Then in this case, we need to supply the reference value at the input. Then you may want to know what is the reference value for the volumetric flow rate and the mass flow rate. And this drawing basically show you example. For example, we keep the height to be constant, control it. Therefore, when this one is controlled at the constant, then the flow rate at the outlet should be constant, right? So if you change the height, then we can vary the reference value for the flow rate, all right? So obviously you see here you must have a feedback control system to maintain the height to be at a constant value, right? Then how to calculate the flow rate here based on the high value H. So actually you can apply Bernoulli equation. You treat this is a 0.1, this is a 0.2. At the 0.1, the flow rate is 0 because the high maintained at the constant. The pressure you know is atmospheric pressure, right? Then at the output here, the pressure is also equal to atmospheric pressure. And then the flow velocity is a variable for you to determine, okay? So this just for you to know, actually you can use the Bernoulli equation to relay the flow rate at the output to the height you need to set, okay? So this is a way for you to obtain a reference value at the input during the calibration process, all right? So after calibration, always remember to do error analysis, all right? So error analysis means, so you have a flow rate on the measurement, you repeatedly do 100, 200, 500, 1000 reading. Then in this way, you can calculate the mean value, standard deviation, etc. All right, and also you can increase the input and then do a reading, then reduce the input, then do the same reading, then do the comparison to see whether there is a hysteresis error or not. All right, so these are the additional tasks for you to do before you can sell your product or let other people to use your product, because the buyer of your product, user of your product need to know this information, right? Okay, so that's all for the study of this lecture. So the key takeaway from this lecture is for you to know the typical application scenario, okay, which need to know the value of free flow rate. And also we have a study a different way for us to do indirect measurement. And in particular, we have a study 3 popular principles for us to follow in order to guide the design of a measurement and the sensor system for free flow rate. Thank you for your attention. I'm looking forward to seeing you in the study of next lecture.